So we'll start with lecture 12 today. Let's do some check-in. So these are generic references for machine learning and CNN. More specific references to publications. We looked at a bunch of them in the last lecture. So today we'll focus on this one, which is a ResNet. We'll also do a recap of the CNN architectures that we've looked at so far. So some of the popular CNN architectures include AlexNet, ZFNet, GoogleNet, VGGNet, among many, and also ResNet, which we'll cover today. And if you see, they're all like improvements on the PlainNet architecture that was proposed a long time back. And all of these are also connected to the ILS VRC challenge, where people were able to challenge themselves to come up with better models that can do better on the top 1 and top 5 accuracy on the ImageNet dataset. And you can also see the number of parameters changes a lot between these different models. Fewer parameters is better because it takes less time to train and also less prone to overfitting. For instance, VGG might be more prone to overfitting than GoogleNet, right? So this is more. So the number of parameters does matter. And yeah, as people have gone through the challenge, they do better on the error rate than the previous year. So there's always some improvement happening. And this is the evolution of the top 1 accuracy across the years. We spoke about the top 1 accuracy being less than top 5, right? Because if you have like 5 things that you predict, your model predicts, the top 5 only needs to get the true label right in one of these 5 slots, whereas the top 1 has to get it right in the first slot. So, having to predict the right class label in the first slot is more challenging than getting it right in the top 5. So for that reason, the top 1 accuracy is always less than top 5. And you can see the top 1 accuracy started at 65%. It kind of kept growing up, and then at this point, it's almost hit 90% as of 2022. So there's been a massive improvement in the top 1 accuracy. You can see AlexNet, VGG, Inception, ResNet, and actually we're looking at ResNet, but ResNext is a improvement on ResNet that we discussed today. And you can see it almost shows up until like 85% here, 2018. And there's like other ones. So there's no end to the kind of models that can do better and better. So if you're interested, I would, just look up these models and understand what they are in your own time. You may not have time to cover all the models, but we're kind of covering a representative set. And you can even try ResNet for this assignment for the mini project because it has some good properties, especially in terms of having deeper layers, which we'll talk about today. So top 5 accuracy, as we know, top 5 is always better than top 1. So you see in the evolution, we start 85% for AlexNet. And as of today, I think we are close to 98% or something, which is pretty high. So yeah, this is also gone up quite a bit. So if you look at ResNext, I think it's close to 96% in 2017. So already come pretty close. Yeah, there's so many submissions that have been made over the years. Okay. So yeah, we've looked at AlexNet, ZeefNet, GoogleNet, VGNet. So we'll look at ResNet today. So just as a recap, it all started with LayNet, which was, so the naming also is based on who came up with it. So Jan Le Kun came up with the LayNet. So then people have started naming after who came up with it. So LayNet was pretty simple, but it was one of the first models that used convolution and subsampling or pooling uh, in the neural network, and it didn't have too many layers, 5 layers, pretty straightforward. But this was kind of like the basis for improvements in the subsequent models. So AlexNet is a direct improvement on LayNet, and has deeper layers, and it incorporates ReLU. So these are like two changes. And then ZFNet is an improvement on AlexNet. And as we discussed last time, it's mostly hyperparameter tuning or tweaking in the AlexNet. So you can come up with an architecture, but you might not have optimized it in terms of hyperparameters. So number of hidden layers, number of neurons per layer, and things like that. So optimize for it, and then even stride lengths. So these are all hyperparameters that you can tune. So tweaking those, you can get better improvement. So in this case, it's not a significant improvement, but it's still, I guess, did it win the challenge? Yeah, one second. So yeah, it did win the challenge. So 2013. So there was a marginal improvement in hyperparameter tweaking, but it still won the challenge in 2013. So it's good. And number of parameters same as AlexNet, right? And then we have VGGNet. So this was like the first major departure from AlexNet, and it had many more layers of convolution stacked before going to the next layer, before the pooling happened. And it also had more fully connected layers at the end. So more stacking. As compared to AlexNet. Right. And you can see the idea here is you can get better and deeper representations using the stacking, and you can learn more complex functions, provided you don't overfit, because the number of parameters in VGGNet has gone up from ZFNet because you've added all these layers, and especially the last 3 layers of fully connected layers, those are adding to a lot of parameters. And so you have to account for overfitting. But despite all of that, the top 5 accuracy for VGGNet improved from 85.3% to 92%. So that's a significant bump. So using more depth in the layers does help, does matter. Okay, so that's VGGNet. And then we also spoke about GoogleNet and the inception model. And the key motivation is that there is, a lot of fine-grained differentiation between different classes in the ImageNet. So you do need these, the depth of the layers are all, and also more complicated ways to model image, and detect features in images. So you can see GoogleNet here, we spoke about last time. It introduces something called an inception module. That allows the model to learn from not just one kind of convolution, but different size convolutions, right? So you can have a convolution of size 3 by 3, of 5 by 5, 1 by 1, but they're all happening in parallel, and then you kind of concatenate it before going to the next layer. So, and then the model is able to, because this is like resolution, so you can you can look at convolution of 5 by 5 as looking at a more broader uh, portion of the image than just 1 by 1 convolution, which is just looking at one pixel. So you're essentially changing the resolution of the window at which you convolve and allow the model to pick up different pieces of information from these different convolutions as it feels fit. So that's the key innovation with the Inception module. And essentially, although this looks pretty complicated, it's a stacking of these Inception modules along with a few bells and whistles, right? So this is like one of the interesting parts of Inception module as well, is you're able to give early output. So this is like you're predicting early, but you can also predict at the very end. So, and this is a quirk of Inception module. We don't see it in other modules, Inception model. But the idea here is that if you want to predict early and you're waiting for the result at the very end, you can do that. It may not be the most accurate, but you can still get a result. So that's Inception or Google Net. Yeah, so that's great. And then, the architecture is complicated, but then we know how it looks like. So we don't use Inception. The model doesn't use Inception modules to begin with. It starts with standard convolution and max pool. But as you go through the layers, you start introducing Inception more and more. Again, things like this, why not use Inception all the way? These are all trial and error. And you develop intuition after the fact. You try it out and then you explain it. And if it didn't work, you'd explain it a different way. So it's not like people fully understand why certain architectures work, but when they do work, you can explain it after the fact. This is why it worked, and you will come up with a reasonable explanation. And hopefully that explanation also helps you develop newer models and helps you, grow your understanding of DeepNets. So a lot of trial and error in this deep learning world. There's very little theory, but there's a lot of experimentation. So yeah, people were averse to experimentation to begin with. They always, like, machine learning has always been grounded in theory. People have always tried to explain things along with experimentation, and not just do experimentation. But with deep learning, things have changed because the improvements that you can get with experimentation are, far outweigh just coming up with a beautiful theory of why something works and then experimenting. So with deep learning, people have stopped waiting for theory to justify a model. They just say, hey, try it out. If it works, great. If it doesn't work, we'll try something else. That's a nice principle in general, but we spoke about interpretability and explainability of machine learning models, and in that context, explainability is important. Like, you want to be able to explain. So that theory that you might come up with can help you understand why things are happening a certain way or why the model is predicting a certain way. But with deep learning models, that's difficult. So people, you can circumvent it by having separate explainability and interpretability models. We talk about this in the machine learning course that's in the next quarter. But for deep learning models, interpretability is still very important. I think we might touch upon it towards the end of this course, especially for nets. How do you have interpretability? Yeah. So, but it's more complicated because you have so many layers, and how do you take an input that came in like 20 layers before, and then it got transformed to something else right now? Like, what happened in between? Those are not so easy to explain, even with an interpretable model. But there are ways to do it. So we'll talk about it. There's some ways to do it that make it more easier to understand the transformation from input to the output, right? Like one example of this is the Lime model. So you can look this up. So Lime is a model that explains a complicated model. Let's say this is a black box model. Okay, Inception has like 25 layers. And then you want to explain the Inception model. You construct a simpler model to explain this input-output that you're seeing with the Inception. And the simpler model is then going to be able to say, you have these features in your image, which I can explain these features, right? I mean, in terms of convolutions or in terms of edges or whatever, that has led to this output. So you're using a simpler model to explain why a complicated model might have chosen this output. So it's not very accurate, but it still is giving you a sense of what kind of features were probably involved in making the decision. And that can help remove the black box nature of the prediction, right? And help you give more insight into why the model is choosing to predict this class or that class. So that's one such model for interpretability. There's many more models for interpretability, and it's an important question we'll discuss later. Okay. So let's get started with ResNet. ResNet is the winner of, so it's the winner of the 2015 ILS VRC challenge. Okay. And it's also a model that people have used a lot in computer vision, outside computer vision, because it comes with an interesting property that helps you make models more deeper without overfitting and actually getting good predictions. So let's look at what that is. So ResNet, the architecture itself is here. So this is the architecture for ResNet. This is VGG. This is, let's say, PlainNets. And then this is ResNet. Okay, so we may have to zoom in here. Okay, let's zoom in and see what's happening. So VGG, you have convolution pooling, and so on. Notice the output size keeps going down, right? So we start with an 224, so it's like, let me see. Okay, yeah, that's okay. There's 224 by 224, and then there is 112 by 112. And there's 56, and so on. So at the very end, you have 1 by 1, but the depth actually goes up, right? So the depth has gone to 4096. And then it finally goes to 1000. So the depth here is actually helping us with the classes. So you can say this is a way to like understand how these sizing changes, because at the very end, you want 1 by 1 by depth, where the depth is matching the number of classes. So that's a way you can construct these layers. But you will obviously start with, some pixel by pixel. So here 224 by 224, but then you start reducing it from there, and then you get to where you want to be, which is 1 by 1 by the number of classes. So that's how this is structured, right? Okay, so that's VGG. And we saw it has multiple convolution layers stacked before you go to the next output size, and then again stack the convolution layers and so on. If you were to do the same thing with more layers, so this is like 34 layers, then you'd be basically filling in the gaps here. And then you see this /2 is when you shift from one size, output size, to the other. You downsample using pooling, or you can also downsample. I think in this case, the downsample happens through using a stride of 2. So you can either downsample using pooling or use a stride of 2. So in this particular 34 layer, you're downsampling by striding. So there's no max pool in this. There is a max pool here in VGG, but you don't see that here. And essentially you're filling in the gaps, right? So what's the difference between VGG and this one here? You're filling in the gaps with more con nets. So that's why all these gaps get filled up here. And that's how you get 34 layers. Okay, so that's not so bad. It's straightforward. Okay, from here to here, that's where our ResNets come in. Okay, so what's happening in ResNet is this shortcut connection, sometimes also called a skip level connection. So you're taking a shortcut and skipping one or two layers and then connecting it. So we'll talk about the skip connection and what it means. It's pretty interesting. And this is very much connected to what ResNet stands for. Okay, so the difference between this 34-layer plain CNN and the 34-layer residual CNN is essentially the shortcut connection that gets added at many different steps. That's it. This is the only difference, but it is a significant difference that enables you to increase the number of layers without consequences. Right. So we'll talk about this skip connection and what it means. But let's look at some motivation. So ResNet stands for residual networks. So res is basically residual. And what is residual? Residual means something left over, right? So residue is like leftover or like difference. So it's a residue with respect to a reference. So there is a reference, and then with respect to a reference, there is something that's left over. That is the residue. And so it's a residual connection and a residual net or a ResNet. So that's the naming convention that's how ResNet came up. And ResNet has an ability to train deeper networks more effectively than PlainNets. So let's look at why that's the case. So I've referenced the ResNet ILSVRC paper, which we'll be referencing throughout this lecture. And this one is the model that won the 2015 ILSVRC challenge. So the motivation here is if you just take two CNNs, so this is an 18-layer CNN network and 34-layer CNN network with all the convolutions. So essentially this thing, right? Essentially this one, 18 or 34. So let's say you have two different choices. What the authors of this paper observed is as you keep training, the 34-layer model performs worse than the 18-layer model. And this was baffling. And it's not because the 34-layer model is overfitting. So here, the thin line is the train error, and the thick line is the validation error. So you see the train error, the thin line in red, is almost always higher than the blue line, blue thin line. So that tells you that the training error for the 34-layer network is higher than the 18-layer. And the same goes with the validation error. So it is, if it was overfitting, then you will see, a different kind of a curve. So there is something else that's going on, and this is what the authors call degradation. So instead of doing better than an 18-layer model, at least as good, it is actually doing worse. So there is some issue with increasing the number of layers beyond a certain point that the authors hit as a bottleneck in improving the existing model. So that was the whole motivation behind ResNet, is if you want a deeper and deeper model and you think it should do better, but it is not in practice, then how do you fix that, right? So that's the motivation for ResNet. So let's look at an in-class exercise related to degradation, and specifically with respect to this graph. So The authors claim that the phenomenon we see above for plane networks is not overfitting, but it's a degradation, which means there's some loss in performance that's not connected to overfitting. So the question is, this graph actually has a clue on why it's not overfitting, but it's actually degradation. So maybe take a look and see why this is the case. I think there's also an option D, which is none of the above. Let's take like a minute to look at this. Yeah, so let's look at these. Let's look at these options, right? So when you have a high train error for 34 layer versus the 18 layer, this is what degradation is. This is what is referred to as degradation. Is why are you performing worse? Because I'm having a more sophisticated model, so I should be performing better. So that explains degradation. But what explains overfitting? That you're not overfitting. So with overfitting, as the train error keeps going down, the validation error may go up at some point. Remember this graph we had for overfitting is train error. Oops. So train error goes down, but your validation error goes up at some point. So this is validation and train. So there is a point where your training error keeps going down, but your validation error goes up. So you see the thin line here, let's say you are overfitting, let's say the 34 layer model was overfitting, then the thin line in red is going down, great. So that says that the training error is going down. But the thick line is also staying low, so it's not going up. So if it was overfitting, you would see that phenomenon happen. And there is a gap between the validation error and the training error, but we don't see that gap. So this explains that overfitting is not happening, right? If it was, then you would see, things going up. So when you combine 1 and 2, you can say that there is degradation, but it's not due to overfitting. Right? So both aspects explain, this phenomenon in this graph. Okay. So yeah, overfitting or degradation is not the only issue with deep neural networks. People have explored this, and this is in. Okay, sorry. Yeah, in this case, the thin line is train error. The thick line is validation. Okay. So we're saying that for overfitting, we see a gap between a thick and a thin line of the same color. So if it's red, you see a gap there, but we don't see that happening. So overfitting isn't happening. As you train more and more, we don't see that gap. But degradation is happening because the 34 layer, the red line, the thick red line is always higher than the thick blue line. That is a degradation. Like you have a more complex network. It should at least do as well as the 18 layer, right? It shouldn't be worse, but it is worse in both training and also validation. So overfitting is not the only issue with DeepNets. People have had other kinds of issues with DeepNets, and you might have heard this term. And it's also an interview question if you have an interview on deep learning, somewhere people will ask you, what is vanishing or exploding gradients? So this is also an issue that people have had. It's because of the multiplicative nature of, how you go, when you do feed forward, you're actually multiplying weights, multiplying. And so the gradients can explode. When you take the gradient of this whole network, it can explode, or it can also vanish. So When you multiply, let's say I multiply 0.1 by 0.1 by 0.1, so on, I'm going to get 0. So this is vanishing. Or if I multiply 2 by 2 by 2, and so on, that's going to be a large number, and this is exploding. So things can explode or things can vanish. And this is an issue because if you have vanishing gradients, the gradient is conveying information. If the gradient is vanishing, there's no information. If the gradient is exploding, again, you have issues because things are not in scale, and you might have issue with training or convergence. So either way, you have issues. And this is something that people have seen in DeepNets, especially was noticed in recurrent neural networks. So RNN, recurrent neural network, which was used a lot for training natural language processing models. These days, people use LSTM or transformers, and they fix some of these issues that vanishing and exploding gradients that you saw in RNN. So anyway, so this is, we'll talk about this in the next course, but applies more to NLP, the transformer LSTM models. So yeah, so vanishing and exploding gradients can be an issue where your gradients are not contained. They are either diminishing, going to 0, or exploding, and this leads to early convergence. So with vanishing gradient, for example, instead of having something like this, you might have something like this. Okay, so there's with your vanishing gradients, you're not making progress when you should be. And with exploding gradients, you might have other kinds of issues. So this is also an issue that deep neural networks have. However, people have figured out that, well, what does vanishing mean? It means you're going out of, or exploding gradients mean it means you're going out of bounds. So let's do normalization in between, every few layers, kind of do some normalization of the weights. And this will make sure your gradients don't explode or vanish. Okay, so that's called batch normalization. So batch normalization is able to fix this issue of scale in the gradients. Okay, great. So that's a trick that you can use, and people do use it very frequently in deep neural networks. Okay, so despite batch normalization, authors saw a degradation with plain deep nets. So degradation is not something to do with vanishing or exploding gradients. It's just a quirk of deep nets that you're seeing this issue. So that was surprising, and it was also not overfitting. So it's not overfitting. It's not connected to vanishing or exploding gradients. It's a new issue that they came up with, or they observed in the context of CNNs. So the idea, that whole idea of degradation is ideally a deep net should do at least as better as a shallow net, if not overfitting, right? So for instance, if you have 1, 2, 3, 4, 5, this is 1, and then you have 1, 2, 3 layers. I may just say these 2 layers, let them not do much. Let them just take the input here and then just copy it here. So that's the same as a 3-layer model, right? So you can call this an identity mapping. So if this 5-layer network does identity mapping between the 2nd layer and the 5th layer, it reduces to the 3-layer model because it's not doing much in these 2 layers. So if I get some accuracy with a 3-layer model, with identity mapping, I can get the same accuracy with a 5-layer model. So the identity mapping tells you that you can do at least as well as a shallow network. So the issue is with a deeper network, in degradation, the identity mapping is not happening where it should be, and so you're performing worse. So We'll talk about this and how it gets fixed in the ResNet. Okay, so just as a motivation, this is the plain DeepNet on the left, and this is the ResNet. So you see the thick line, which is the validation error for the DeepNet, a 34-layer model, is worse off than 18-layer. So this gets flipped around in the ResNet. So now you see the thick red line is actually below the thick blue line. So this issue of degradation gets fixed between the curve on the left and the curve on the right. And you see this happening for both training and validation. Right. So now we don't have overfitting, we don't have degradation. So ResNet is able to fix this issue, essentially. And they actually use this. So here you see a 34-layer model, but they've actually trained, it's beautiful. They've shown that, well, once you fix this, you can even train a 1,000-layer model and you will do, you'll hopefully do better if you're not overfitting. So you can actually increase the number of layers as much as you want. So this allows people to actually go deeper without facing issues of degradation. If you need to have such a deep network. Okay, so this graph tells us that ResNet has actually fixed the issue of degradation, because now you see the red and the blue curves have kind of swapped positions, and you are doing as expected. So the 34-layer model is definitely better than the 18-layer model in terms of the error. Okay, so let's come to the ResNet building block. So just like we had an inception module that was horizontal and it was able to capture scaling over the input at different levels of scaling, the ResNet is doing the residual learning through this building block. So what is happening here? This is the input and this is the output. And this is like a module that's sitting inside this 34 layers, right? It's somewhere in between. So if you didn't have this connection, then it's a plain neural network. With this connection, you have a residual neural network. So what is this saying? It's saying, let's call this transformation from x to this point f of x. We're just going to copy x over after these transformations. So x just gets copied over here, and then we're going to do a summation here. So this is an identity mapping, right? Because you have not transformed the input. You've taken the input as it is and just copied it over, but you've added to it a residue. So you can say f of x here is a residue, and then x is your input, and your output is x plus the residue. Okay, so at this point. So the x here, is because of identity mapping. So like we spoke about, if you were to just not do anything between the second layer and the fifth layer, you would just copy over the input and then make it the output, right? And that would be equivalent to a 3-layer model. So that's what the residual connection here is doing. So this is called the shortcut connection or skip level connection, because there's a shortcut between the previous layers and the current layer. You're skipping a few layers. So if it is the case that in this deep neural network, you're not doing much, then you can just set f of x to be 0, and that captures that aspect. For instance, between 18 and 34 layer, I'm not doing much in between. I should be as good as 18-layer model, then set f of x for those in between layers to be 0, and then let the model learn that, and that residue would be small. And then you would just output x. But if there is something really going on, then f of x would not be 0. There is something actually going on, so it's going to learn that as well. So that's it. It's a simple addition of x and f of x. And here x is a reference, and f of x is the residue. So f of x is a residue with respect to a reference, which is your input. And hence it's called a residual neural network because you have these residues coming in between. And in practice, the authors also saw that these residues are actually small, which tells us that the model is doing something in between all the layers, but only as much as is needed. It's not changing things a lot. It's changing things as much as is needed, and hence you only change as much as the residue indicates, which is a different thing from if you didn't have this reference. So let's call this h of x, output h of x. So here h of x is defined in terms of x and a residue. You could also just not have this skip connection and just train a plain model, and maybe you can still learn the h of x, but in practice it doesn't happen. So it's easier to have the model go through this residue than not, because that's a quirk of deep learning models is it's based on optimization and local optima, and you need to kind of guide it. So here this guidance is actually helping it learn better on deeper nets. Okay, so that's a little bit on the residual building block. So the key takeaway here is you have a reference and you have a residue, and the residue and this setup helps the model learn residues as needed, or just copy things over from the previous layers, leaving things untouched, so that you do at least as well as a shallower network. Okay. So you see these are the shortcut connections that, and there are these dotted lines as well, which is optional, but you see this happening. And then you can also have like longer ones, like you can start here and go all the way here. So you can have longer, so that those are like hyperparameters, and the authors have also experimented with some of that. But typically like 2-3 layers, you kind of have an input here and then you copy it over here. And then there is this would be your f of x. And then, so as you increase the number of layers, these residual connections, this skip connections do play a big role, because maybe you're having small incremental changes and you don't want those changes to get lost. And you want to have a model that does better with fewer changes, right? So this is able to capture that. Okay, so to understand the residual ResNet building block, let's look at an in-class exercise. So this is a little bit of a kind of a mathematical in-class exercise, but it helps you understand this building block. So let's say we have a ResNet building block as above. The only thing different from a plain net is a shortcut connection. So this is the shortcut. So if you didn't have this, it's a plain deep net, plain net. Otherwise, you have a residual net. So so the question, so notice here you also have a ReLU here. So there's a ReLU function here, ReLU function here. The question is, if you have weights assigned to the first and second layer, and assume it's a feed-forward network, so we don't have to worry about convolutions for now. Just assume it's just a feed-forward network. You're just multiplying things, and sigma represents the nonlinear ReLU activation. How would you represent the output of this block in terms of the input and the weights and the sigma? So that's the question. So let me just add some notation here. So let's say the weight layer here is W1, this is W2, this is sigma, this is also sigma. Okay. And then you have F and you have X. So given all of this, there is a way to go from here to here. So the question is, what is that in terms of all these components? Let's just take a look and maybe take a minute or two to just work on that. Okay, so hopefully you had a chance to look at this. Yeah, this makes sense, right? Because your last transformation is a ReLU, so that's going to show up outside of everything else you've done. So, and then you have the summation of, so what is f of x here? It's W2 sigma W1 of x. Yeah. So you take the input, transform it by W1. And since we said it's feed forward, just kind of multiply it, W1 times x. And then you apply a relu on it, so sigma of that. And then you apply W2 to this transformation, these set of neurons, and then you get f of x. But then you add to that x, but then again you transform it with a relu. So yeah, and this is just one block. So imagine you have all these other blocks, and then so that's where, if you look at PyTorch, it does automatic differentiation. You just have to specify the layers. It's able to figure out these functions, and then it uses rules of composition to understand how to compute the gradient. And then the gradient gets used in stochastic gradient descent, and then your training happens. And then that's how you see that curve. So, but it's important to know this mapping, and it's happening behind the hood. When you set up your model in your PyTorch, it's already having this mapping in mind, and then it's able to compute the gradient based out of that. So, but it's important to understand, when you look at it, you're like, what is the function here? So this is a good exercise to understand, what exactly is happening between the input and output. Yeah, so no matter what the weight layers learn, the identity will always reflect. Yes, correct. And the key thing here with residual net is that it reflects better than with a regular network. And somehow identity is something that's useful in some of the layers because nothing much is happening. But a regular plain network is maybe failing to learn that identity mapping, although it can learn as well, but it's failing. And that is why you need to guide it with this residual connection, the shortcut connection. So that's where the degradation is happening. Yeah, and this is also a quirk of neural networks because there is local optima, and local optima depends on starting points, it depends on network structure, and certain network structures are more amenable for certain local optima. So because of the optimization that's happening, this kind of a transformation helps the model get to where you want it to go more easily than a regular net. So this is, you can say, a quirk of the neural network. Deep neural network is the optimization may not be happening as well. So the degradation is actually connected to optimization. The optimization is not happening as it should be, or it's getting stuck. So the engine behind the training is getting stuck somewhere. And this is able to guide it towards getting unstuck and doing its job better. Yeah. Oops. Okay. I have to charge my iPad soon. This is kind of a breakdown of the architecture of the ResNet for different layers. So 18 layer, 34 layer, 50 layer. So let's say you look at the 34 layer, you see convolutions of different sizes, 3 by 3 by 64. This is the depth, as you know, and this is the size. And then there's 3 of them, there's 4 of them, there's 6 of them, there's 3 of them. So if you add these up, 3 plus 4, 7 plus 6, 13 plus 3, 16, but then there's 2 of each. So that's 16 times 2 is 32. So roughly you get 34, right? Close to 34. So that's how the math adds up here. You look at 101 layer, the same thing. You can just add these things up. And then at the very end, you want to get to a 1 by 1 by 1000, because 1000 is the number of classes. So again, you would do some kind of pooling. So the pooling is happening over 7 by 7. So you take the 7 by 7, do an average pool, take the average of these 49 numbers, but you have 1000 depth. So you get 1 by 1 by 1000, and then you may make a prediction. The size of these networks is given in terms of flops, but I think the number of parameters is for a 34 layer model might be in the order of 10 million or 20 million. I'm not exactly sure. And it just keeps increasing, but not by too much. The reason is the intermediate layers do not add as many parameters as the final layers. We spoke about this. When you go from a conv layer to a fully connected layer, that's when the jump in parameters happen. The intermediate layers do add, but not as much. So you will not see a very big jump as you go from one model to the other in the number of parameters. Okay. So we looked at the results here. The ResNet does better. So this is where you see, okay, with the use of this shortcut connection and residual network, the degradation issue, which is actually an optimization issue, gets fixed. And now you're seeing things are in the right place. So a 34 layer model is doing at least as good as an 18 layer model, because maybe the INT mapping kicks in at the right places, and then you're just copying things over. And then wherever you need to make improvements, you are making those improvements, and so you're doing better. Okay, great. So this issue gets fixed in the ResNet. And as compared to Inception and VGG, you can see the errors have also gone down. So this is much lower, significantly lower on top 5, but also on top 1. So the top 1 accuracy and the top 5 accuracy. So 19.38 error means your accuracy is 80%, right? And 4.49 error means the top 5 accuracy is 95% or 96%. So this is, this makes sense. 4%, okay. You see how many slides we have left? A few slides left. So maybe we can make it through. So yeah, so you can see this whole section is kind of just ResNet with different number of layers, 34, 50, 100, 150. So as you increase the number of layers, you're still not overfitting, but you're improving the performance. So more the layers, the better, but only if you do it right. So the ResNet has fixed that issue of doing it right by having these shortcut connections. And you can see there is definitely improvements happening. So, sorry. So you can definitely see the improvements are happening as you increase the number of layers in the ResNet. I mean, there's a big improvement from 34 to 100, but from 100 to 150, you don't see a very big drop. So the returns start to diminish. So there is like a sweet spot, like maybe after 200, you don't see a big improvement. And this is on the validation set. On the test set, the ILS-VRC sees a 3.5%, 57% error on the top 5 metric. And this is as compared to Inception with BN refers to batch normalization versus VGG 6.8, right? And they also tested on CFAR. So CFAR is another image set. It has about 60K images, like 50K for train, and then 10K for test. And then CFAR, they have CFAR different, CFAR 10, CFAR 100. So 10 refers to the number of classes. So they have roughly about 6,000 images per class. And then 10 classes, so 60,000 images. 50K of them go into training and 10K go into test. So on the CFAR 10 data set as well, the ResNet 110 does well. Okay. But the curious thing here is ResNet 1202. So they use 1200 layers in this ResNet, which has 20x more parameters. Okay, so here it says that there's like 0.5 million parameters for 32. So maybe the 10 million that we spoke about earlier is with more bells and whistles, but you can see between 110 and 1200 layer ResNet, there's a roughly, what is this like? Yeah, about 10x more parameters. So the error actually went up from here to here. Then we'll talk about this. We spoke about degradation, so then what's going on here? Is there a degradation or there is something else going on here that the error has actually gone up? Okay. So far all of this makes sense, but here, what's going on, we'll talk about that. Okay, so yeah, so this is again a result on CFAR. You see with PlainNets, as you increase the number of layers, the error is actually going up. So this is not good. But with ResNet, as you increase the number of layers, the error is going down. So this is good. So again, on a different data set, not just ImageNet, maybe you're over optimizing on ImageNet, try on something else and see if the phenomenon is happening. And you see the phenomenon is actually happening on different data sets. So this is a more, they've uncovered something more fundamental that, if you want to increase the number of layers, then do the ResNet, and then you're able to fix the issue of degradation, not just on ImageNet, but also on CFAR and other data sets. And this is this concept of being able to go across different data sets and do well is called generalizability. You're able to generalize to different data sets, to different kinds of settings. So your model is not very specific to one data set. It actually works on other data sets as well. So you can see from this graph that the ResNet is generalizable. It is doing well on other data sets as well. Okay, so we spoke about this. The funny thing happening here is when you go from 110 to 1200, the error has actually gone up. So let's talk about that. Let's look at this figure here. You see a comparison between ResNet 110 and ResNet 1200. There's a thick line and a thin line. So let's say focus on the thick line that corresponds to validation. The question is, the 1000-layer ResNet has a worse validation error than a 100-layer ResNet. So what is the likely explanation for this? Maybe take a minute to look at this and share your answer. Yeah. So in this case, actually, what happens is, what's probably happening is, it looks like degradation. So, there might definitely be some degradation happening, but then ResNet is supposed to have fixed it. You're using a ResNet, right? So if, but you're still seeing it. So then you say, well, maybe there is something else going on. So if you, as we spoke about, the number of parameters in a 1200 neural network model is like 10x that you see in a 110 model or a 30 model. So you've actually increased the number of parameters, and that might indicate overfitting as well. So as your train error is low, but your validation error has actually gone up, right? So here with all these other models, your train error is going down, but your validation error is also going down. But here it has flipped. Your validation error has actually gone up, even though your train error has gone down. So this is a case where your validation error is actually growing as your model becomes more complex. So that indicates that you're starting to overfit. And yeah, obviously overfitting is also connected to optimization, but it's more of overfitting than degradation. There is a degradation, but the degradation is connected to, right? That's a good question, John. Is one connected to, is just an observation? Yeah, one is an observation. You can say, well, let's say one is more of degradation, but no overfitting. Maybe that's a better choice for one. And second is degradation with overfitting. And third is optimization issues. So then you would say there is degradation because, yeah, the error has gone up, but that is not connected to, that is connected to overfitting. It's not connected to an optimization issue. So And we see that because as the train error goes down, the validation error is actually going up. So that explains there is overfitting happening. So yes, you can train deeper and deeper models, but notice at some point the number of parameters is going to grow significantly as compared to the number of data points. And so you will hit that regime of overfitting sooner or later. Even if you use dropouts and other tricks, you're going to hit that. So there is going to be a limit to the number of layers that you can use. So even with ResNet, they just train 1,000 layers just to see, what happens, and they figure out that, okay, at some point we enter the regime of overfitting, and that's why we are performing worse here as compared to 110 layer model. Okay. All right, so we'll actually stop here for the day. In the next lecture, we'll look at pre-training CV models, and we'll move into object detection and image segmentation, which is our next topic in computer vision. Okay.
Thank you.